Okay, for this section 5.5, I'm going to do a little bit of review of what we covered before our break and kind of set us up for the last two parts, ionization energy and electronegativity. So going back and looking at, we were explaining the location of the S, P, D, and F block elements on the periodic table based upon electron configuration in these suborbitals, and we explain why elements in the same group have similar properties. One of the things we want to look at, we have metals, nonmetals, metalloids, and then man-made elements. So the question, what is silicon, Si? There it is right there. What is an example of? Metal, nonmetal, intertransition metal, or metalloid? If you said metalloid, you're right. Again, remember there's a zigzag or staircase that runs down through the periodic table. Everything above and to the right are nonmetals. Everything below and to the left are metals. The ones touching the staircase, with the exception of aluminum, are metalloids. It means they can't quite figure out whether they're a metal or nonmetal. The gray ones you see here are man-made. There's actually more of those, but a lot of these are man-made as well. And also remember the valence electrons, those are the electrons that are in the highest of any energy level within a given atom. And by energy level, I mean period or row on the periodic table. And there's helium. It, along with hydrogen over here, are on the first row or the first period. So if you look at helium, it's got 2 protons, 2 neutrons in its nucleus. But we're looking at the electrons now. It only has 1 ring of electrons. So anything that's as high as it's got, because that's all it has. Same with hydrogen. So that's its valence electrons or valence shell. So helium has 2 electrons. And we knew before from the alpha, 1 up, 1 down. That's the lowest energy level. Those are its valence electrons. So it has 2 VEs. And for giggles, if we go down and drop a row to the first element, lithium, it's on the second period or second row. That means it has 2 rings of electrons. And since it's in the first position over there in the S block, it has a 3rd electron. It sits on that. Therefore, it has 1 valence electrons. The 1 on the inner rings do not count. They are core electrons. You can never get enough energy to get them apart and use them. Atoms in the same group or column have the same chemical properties because they have the same number of valence electrons. So we look just at group 1, everybody in that first column. On that first row is hydrogen, and helium would be next to it. But in that first group, it only has 1 valence electron. And it only has 1 ring, so it's its valence ring. If you go to group 2, it has 2 rings for lithium, but again, only the one on the highest or the farthest out ring is its valence ring or valence shell. It also has 1 valence electron. If you go to the 3rd row, it has 3 rings. 1, 2, 3. But even with all the electrons in the inner rings, only the outer one counts. And that's why it's there. It has 1 valence electron. If you move on down that row, you're just adding number of rings. 4 rings, 5 rings, 6 rings, 7 rings. But in the last or the highest energy level, the farthest out ring, it'll only have 1 electron. That's why from a chemical standpoint, they only have 1 to give, to bond, and to do things. That's why they're chemically very, very similar. Looking at the S, P, D, and F block on the elements, most of the time, guys, for us, we're going to be dealing with the S and Ps. Very seldom do we do the Ds, but they do exist for us on this level. Blocks on the periodic table represent the atom's energy sublevels and how they're being filled with valence electrons. If you remember from looking at a 3-dimensional standpoint, how do these electrons go around the nucleus? Since it's 3-dimensional, we have an x-axis, up and down y-axis, and then kind of coming out of the screen or into the screen, a z-axis. It's the best I can do from a two-dimensional representation of a 3D situation. The closest to the first is 1s. That's that first row. There's only hydrogen, helium. They only have s block elements. And we said before, to calculate the number of electrons this can hold, on the first level, you take the energy level, 1, equals 2n squared. You put the n in for the energy level of 1. 1 squared is 1 times 1, which is 1, times 2 means the most I can put is 2 electrons on that first energy shell. That's why there's only 2 boxes on that first row, one for hydrogen, one for helium. There's hydrogens, there's heliums. It's full, it's stable. If I go to the second row, n equals 2, it has 2 suborbitals, s and p. So if again I look at the second energy level, I put that in for n. 2 squared is 2 times 2 is 4. 4 times 2 is 8. So it can hold 8 electrons. Where do they go? In the 2s, because we're on the second row, so I got to go through the s block first. S can only hold 2, but I still got 6 more, up to 6 more. That's when they go on these little dumbbell shapes, or the lobes. 2px in the one direction, 2px in the other direction. So that lobe can take 1 electron. There's 5. There's 6. I can go in the y direction. 7. Notice they're a little bit farther out. Takes a little bit more energy to put them out there. And then in the z directions. 7, 8. So the most I can take is 8. 2 on the 2s plus 8. And that's just for the second row. Everybody on the second row all have that inner 2 plus up to 8 more. So I can get up to 10 electrons if I'm on the end of the second row. 2 plus 8. So let's look at the periodic table. This is our Bible. Blocks on the periodic table represent the atom's energy at sublevel, again with valence electrons. First off, again, review, we're going to look at the S block. That's groups 1 and 2. That's these guys. And again, group is like a column. You go with 50 of your friends in a group to the basketball game. Some are going to sit above you, some are going to sit below. Groups go up and down vertically. There's group 1, there's group 2. For every element in the first group or the first column, no matter how many rings of electrons they may have, there will only be 1 electron in their respective outermost or highest energy level ring. They will all have 1 valence electron. So everybody in that column, that group, will only have 1 valence electron in its outermost ring. Group 2, no matter how many rings of electrons they may have, there will only be 2 in their outermost ring, or 2 valence electrons. That's the S block. The P block, groups 13 through 18, but we're not going to include helium even though it's over there. Typically helium would be sitting over here in the S block. So we'd move it over here. So we're just looking at below helium. So group 13 through group 18, that's that block, the P block. That has a little stair step in it. Every element in the 13th column, no matter how many rings of elements, so as I'm going down, I'm adding rings, 2 rings, 3 rings, 4 rings, 5 rings, 6 rings, no matter how many rings of electrons, their outermost ring will only have 3 valence electrons. That's the 3 right here. Take 13 minus 10, you get 3. All the way over to group 18, they have 8 electrons in that group. So no matter how many rings of electrons they have, whatever their outermost ring is will only have 8. So for n equal 1, or the first period or first row, that's these guys, there are no P block elements, just for the first row. If I go all the way across, there's nothing there. So there is no P for the first, just S. For the group 18 or noble gas elements, that's these guys over here. Helium is a noble gas, but it only has 2 electrons, so it doesn't really fit in this description. Group 18, both their S and their P blocks are full. And again, helium being the only one with S because it only has 2 electrons. So if I'm going on, starting with the second row, I'm going all the way over the end, the S and the P will be filled. Again, Helium is only got an S. D block, that's groups 3 through 12. These will all fill their higher energy level S block sublevel first. I'm starting on this row, the fourth row. That's where I got a D block. And then begin to fill, or partially fill, the slightly lower energy level in the D block, N-1. So for example, vanadium. You'll find it over here on the periodic table. It's the third one in the D block. It's the fifth one over, but the third one in the first row. It's going to fill the lower S first, 4S, and there's 2 boxes here. So it's going to fill, this is the fourth row, S, 2, it's got 2 there, but it's also got 3 additional electrons. So we take the N4, when we get the D, you have to subtract 1. So 4 minus 1 is 3. It's in the D block, and it's the third box over. So it's 3D3. So this one for vanadium is 4S2, 3D3. The F block, rows 6 and 7, are called the lanthanide, La, and actinide, AC series. That's those guys there. They actually was squeezed in on rows 6 and 7. There's lanthanide. It's in the D block. But everything that comes after that is the lanthanide series. It was squeezed right up in here if it could. So that's actually row 6. It's got 6 rings. And the actinide, which is in the D block, but everything after it through here is the actinide series. That was squeezed in here. It has 7 rings. Those guys in the F blocks, the electrons do not fill in a predictable manner. You'd have to be into AP chemistry or dual credit chemistry before you'd actually be worried about something like this. So again, that's the series: S block, D block, P block, F block. Helium belongs over here in the S block when we're talking about electron configuration for valence. So which of the following is not one of the elemental blocks on the periodic table? The S block, the D block, the G block, or the F block? If you said the G block, ooh, that's wrong. If you said the G block, you'd be right. F block is on the periodic table. And which block spans 14 elements? The S block, the P block, the F block, or the D block? Span means from side to side. If you said the F block, you'd be right. There's 14 elements across. And that's